The speed of light is constant, that is, it remains exactly 299,792,458 meters per second in vacuum. For object moving at high speed, there must be a dilation in time and contraction of length. In this video, we are going to discuss about these two concepts. First, let us discuss about time dilation. For that, let us take an object labeled A, B, C, D. So let's say that this object has a height of 50 into 10 to the power 8 meters. That is this height. And here light is emitted from E1, reflected back at M and detected at E2. So the distance traveled is equal to 2 into 50 into 10 to the power 8 meters. That is equal to 10 to the power 10 meters. And the time taken is equal to the distance divided by the speed. And we know that the speed of light is equal, which is c is equal to 299,972,458 meters per second. So if we do the calculations, we can find that the time taken is equal to 33.356409525 seconds. So this is the time taken for the light to come from E1 to M and back from M to E2. Now we'll discuss about when the object is in motion. Let's say that it is moving at a speed of 2 into 10 to the power 8 meters per second. So in this case, instead of finding the total distance covered by light and dividing it by its speed, we know this distance, so we can just find the vertical component of the velocity of light and divide it to find the time taken. So when the box is in motion, light will be traveling from E1 to M and back from M to E2. But for the perspective of a person who is outside the box, it will appear to travel in a diagonal path. That is like this. So light is traveling in a diagonal path and the horizontal component is this. And the V horizontal is equal to 2 into 10 to the power 8 meters per second. And the speed of light is here c, and through trigonometry we can find the vertical component of light. So now we'll split the velocity into its vertical and horizontal components. So the box is traveling at a speed of 2 into 10 to the power 8 meters. So the VH, or the horizontal component of velocity, is equal to 2 into 10 to the power 8 meters per second. And we know c because c is always constant. So we saw that light was traveling diagonally. So this is the path of light. So this will be equal to c. And let's call this angle theta. So this value is equal to c cos theta. So this value is equal to c cos theta. So by calculation we can find the value of theta. And then we'll find the vertical component of velocity. This will be c sin theta. After we find the vertical component, we will divide it. We'll divide this vertical component from the distance to find the time taken. After we find the vertical component, we will divide this from distance to find the time taken. So let's first find theta. So c cos theta is equal to 2 into 10 to the power 8 meters per second. Therefore theta is equal to cos inverse of 2 into 10 to the power 8 meters per second, divided by c. So implies that theta is equal to 48.15149,778 degrees. So now we'll find c sine theta, which is this vertical component. So c sine theta is equal to 223,328,273.8 meters per second. So in the second case, the time taken is, let's say, is t2 is equal to this distance, that is 10 to the power 10 meters, divided by this speed. So that is going to give us exactly 44.77713,815 seconds. So if we find the ratio of time to find the ratio of this time to this, it will be equal to 1.34284701. Now we will find the contraction of length. So we have the box A, B, C, D. Here light is emitted from E1, reflected at M and detected back at E2. The length of DC is equal to 50 into 10 to the power 8 meters. And this box is traveling at a speed of, writing it here, 2 into 10 to the power 8 meters per second in this direction. So, for the perspective of a person inside the box, the distance traveled by light is the E1 from E1 to M and from M to E2. So that is 2 into 50 into 10 to the power 8 meters, which is equal to 10 to the power 10 meters. And if you need to find the time, that is equal to the distance divided by the speed of light, which is c. And we know that c is equal to 299,792,458 meters per second. So this is going to give us a time of 33.356409525 seconds. And when the box is in motion, and for the perspective of a person outside the box, the distance traveled will be this distance plus the distance traveled by the box. So for that, we are going to find the contraction in length of the box. Let's say that d dash is the new length and x is the contraction of length. So d dash is equal to 50 into 10 to the power 8 meters minus x. And let's say that the time taken for light to go from E1 to M is equal to T1. So T1 is equal to 50 into 10 to the power 8 meters minus x divided by c minus 2 into 10 to the power 8 meters per second. We are subtracting this because both the light and the box are traveling in the same direction. So we are subtracting this from c. And T2, let's say it is from the time taken for light to travel from M back to E2, is equal to 50 into 10 to the power 8 meters minus x divided by c plus 2 into 10 to the power 8 meters per second. Here we are adding these numbers because the light and the box are traveling in opposite directions. In the case of dilation of time, we had found that here the total time taken was 44.77713 0.815 seconds. So the T1, T2 will be equal to this. So we can write this is equal to 50 into 10 to the power 8 meters minus x divided by c minus 2 into 10 to the power 8 meters per second plus 50 into 10 to the power 8 meters minus x divided by c plus 2 into 10 to the power 8 meters per second. So through solving we can find that x is equal to 1,275,285,321. So d dash, or the length after the contraction, would be 50 into 10 to the power 8 meters minus this. So that is 3,724,714,679 meters. So if we take the ratio of this length to this length, we will find that it is equal to 1.342384701. And this, if you recall, was also the ratio of dilation of time. So the ratio of length contraction and time dilation are the same.